Hello everyone. In this video, we will study about the next important type of turbine, which is Francis turbine. Up to this video, we have covered the Pelton turbine, also inward and outward flow radial turbine, inward and outward flow reaction turbine. Sorry. Now in this video, we will move further for the Francis turbine. In the classification part, I have explained what is Francis turbine. I'll repeat that. Francis turbine is the inward flow reaction turbine having the radial discharge at the outlet. Okay, radial discharge means the value of beta will be 90 degrees here, and also the VW2, that is whirl velocity at outlet, is 0. Okay, that means the radial discharge at outlet. And also the Francis turbine is inward flow reaction turbine. Okay, this name, that is Francis turbine, is the name um, which is given after the uh, American engineer, which is J.B. Francis. Okay, he designed that inward radial flow reaction type of turbine. In modern Francis turbine, the water enters the runner of turbine in the radial direction at outlet and leaves in the axial direction at the inlet of runner. Okay, now here if you see that in this modern Francis turbine, the water enters in radial direction and leaves in the axial direction. That means the direction of entering and direction of leaving of water from the turbine is different. Okay, it is not entering in the same direction as that of leaving. So this is also, that is modern Francis turbine is also a mixed type of turbine. Okay, it is also a mixed type of turbine. Now, the velocity triangles, if we are going to draw the velocity triangles for inlet and outlet of Francis turbine, then it they should be drawn in the same manner as that of for the uh, other types of turbines in the same inward flow and outward flow. The way is same here. Only the thing is that Francis turbine, as I have already explained, Francis turbine has the radial discharge at outlet. Okay, so the value of whirl velocity at outlet will be 0, that is VW2 will be 0, and also the value of beta for outlet is 90 degrees. Okay, this type of example or numerical we have covered in previous video. So for velocity triangles, you can see the diagrams of that. uh, these are simple, only you have to consider beta 90 degrees and VW2 equals to 0. Okay, as the discharge is radial at outlet. Now because of this, work done by water on the runner is rho q vw1 u1. Okay, this is also covered in previous numerical. uh, in usual manner, we are finding the work done in the by using the relation of rho q vw1 u1 plus minus vw2 u2. But here the vw2 value is 0, so the relation is only rho q vw1 u1. Okay. Also, the remaining hydraulic efficiency and the work done per second per unit weight of water striking, the relations for these two also changes, and only VW1 U1 will remain in that relation. Okay. Now, the important relations for Francis turbine. Okay. The relations are first the ratio of width of wheel, to its diameter, that is b1 by d1 is given as n. Okay, b1 by d1 is given as n. That means this ratio, which is width to the diameter ratio of wheel, is n, and the value of it is varies from 0.10 to 0.40. Okay, this ratio will vary from 0.10 to 0.40. Also, the flow ratio, the relation for flow ratio is, you have studied it, which is vf1 divided by root of 2gh, that is flow velocity to the velocity root 2gh. Okay, this flow ratio, the value of flow ratio will varies from 0.15 to 0.30. Okay, this is the limitation for your flow ratio, important factor for flow ratio. Secondly, speed ratio is given as u1 divided by root 2gh. Okay, and the value of it is varies from 0.6 to 0.9. Okay, these are the important points of the turbine, which is Francis turbine. Now we'll move further for the now we will move further for the numerical of your Francis turbine. Okay. I hope you understood what are the important factors of Francis turbine. Also, the important formulas. The formulas are almost same as that of for the used for the remaining type of turbines. But only the thing is that you have to consider the outlet discharge is radial. Okay, so the first numerical is a Francis turbine with an overall efficiency of 75% is required to produce 148.25 kilowatt power. It is working under a head of 7.62 meters. The peripheral velocity equals to 0.26 root 2gh, and the radial velocity of flow at inlet is 0.96 root 2gh. The wheel runs at 150 rpm, and hydraulic losses in the turbine are 22% of available energy. Assuming radial discharge, you have to determine first guide blade angle, the wheel vane angle at inlet, diameter of wheel at inlet, width of wheel at inlet. Okay. Now first you have to find out the guide blade angle. So guide blade angle is nothing but alpha. Wheel vane angle at inlet is nothing but theta. Diameter of wheel at inlet is d1, and width of wheel at inlet is B1. Okay, so alpha, theta, D1, B1, these are the values you will which you have to find out. Okay, now in this problem, the turbine is your Francis turbine with an overall efficiency of 75%. So eta O is 75%. Here eta O, that is overall efficiency, is 75%. Also the power given is 148.25 kilowatts. Okay, now this power is um, they have mentioned that the Francis turbine with an overall efficiency of 75% is required to produce 148.25 kilowatt power. Okay, that means this power is your shaft power. Now this turbine is working under a head of 7.62 meters. That means H is given as 7.62 meters. Also two velocities are given. First is your peripheral velocity. Peripheral velocity is nothing but your u, that is u1, and the radial velocity of flow at inlet, that means velocity of flow, which is vf1, is given as 0.96 root of 2gh. Now if you see here, the velocity is given in terms of h. Okay, so here the actual value of velocity is also to be determined. Okay, now here they have given it in the terms of h, that is in the terms of formulas. So substitute the value of head in that velocity. You will get the value of peripheral velocity u1 equals to 3.179, and the velocity of flow at inlet equals to 11.738 meters per second. Okay, this is about the peripheral velocity and the velocity of flow at inlet. Now the second term they have given is wheel runs at 150 rpm. That means the speed is given as n equals to 150 rpm, and also the hydraulic losses of turbine are given, which is 22% of available energy. Okay, the hydraulic losses are 22% of available energy, and the discharge is radial at outlet. If this is not given, that is the outlet discharge is radial, then by default you have to take it the radial discharge, because Francis turbine is having the outlet discharge as the radial discharge. Okay, so because of that radial discharge, VW2 will be 0 and VW1 will become VW2 will become VF2. Okay, now they have given the hydraulic efficiency. Uh, they have given the hydraulic losses and head at inlet. So we can find out. So that we can find out the value of VW1 as hydraulic efficiency can be find out by using eta H. Eta H will be total head at inlet, total head at inlet minus hydraulic losses divided by head at inlet. Okay, total head at inlet minus hydraulic losses divided by head at inlet. This is the general formula for hydraulic efficiency. Now here total head at inlet will be H, Okay, and the hydraulic losses are 0.22 of H. Okay, and the head at inlet will be here again H. So this hydraulic efficiency will become 0.78. Hydraulic efficiency, by using this formula you will get 0.78. Okay, but the hydraulic efficiency for Francis turbine can be find out by using the formula eta H equals to VW1 U1 divided by GH. Okay, VW1 U1 divided by GH. In this, the H is known value, VW1 you have to find out, U1 is known, and eta H we have find out as 0.78. Now by using this expression, substitute the values here, you will get VW1 as 18.34 meters per second. Okay, this will be your whirl velocity at inlet. Now the whirl velocity at outlet is 0. Okay, but why we have find out this? For finding out the value of alpha. Okay, the VW1 value is this whole value of triangle, whole side of triangle, and this vf1 we have they have already given, so we can find out the alpha value by using tan expression. Okay, tan of this triangle. So first thing is the guide blade angle, that is alpha. From this inlet velocity triangle we can find out alpha in the terms of tan alpha. Tan alpha is opposite side, that is vf1 divided by your adjacent vw1. Okay, now here opposite vf1 they have given 11.738, and the value of vw1 we have find out here, which is 18.34 meters per second. So inverse of this will give you alpha. Alpha equals to 32 degrees 37 minutes. Okay, 32 degrees 37 minutes is the guide blade angle at inlet, which is alpha. Now the second question is, we have to find out the wheel vane angle at inlet. Wheel vane angle is nothing but your theta. Okay, now for this theta, if you see here, this theta can be find out again by tan expression, because vf1 value is known. Okay, here relative velocity is not known, so we have to use tan expression of this. Now for tan expression we need to find out this side of triangle. Now this side of triangle can be found out by using vw1 minus u1. Okay, this whole side minus this u1 will get you the value of this side. Okay, now the value of tan theta, here the expression is written vf1 divided by vw1 minus u1. Okay, vw1 value is 11.738, and this subtraction is written here. You will get the value of theta as tan inverse of 0.774, will give the value as 37 degrees 44.4 minutes. Okay, 37 degrees 44.4 minutes is the value of wheel vane angle at inlet. Wheel vane angle at the inlet. Now the third question is diameter of wheel at inlet. Okay, diameter of wheel at inlet, which is d1. The value is d1 here. It can be found out by using the relation as u1 equals to pi d1n divided by 60. Pi d1n divided by 60 is the diameter of wheel at inlet. Hmm? Now, by using this, the diameter of wheel at inlet can be found out as d1 equals to 60 u1 divided by pi n. Here, the speed is given as 50 rpm. u1 we have find out, so substitute the values of all the terms. You will get the value of d1 as 0.4047 meters. Now the last is width of wheel at inlet, which is b1. Width of wheel at inlet b1. Now for this, firstly b1 will be the term which comes in the discharge expression. So for that purpose, first you have to find out the value of discharge, because in whole uh, problem they haven't give any value or hint for discharge. So by using the expression of overall efficiency, we can find out the value of discharge, because the expression for overall efficiency is shaft power divided by water power. These terms about the efficiencies of turbine. In first video I have in first video of this module, I have explained the formulas and expressions for the all the efficiencies of turbine. In that, the overall efficiency is found out by using shaft power divided by water power. Okay, shaft power value they have directly given, but water power we can find out by using rho g qh divided by 1000. Okay, rho g qh divided by 1000, in which q is unknown. Okay, h is known and remaining quantities are constant, so q is only unknown here. So substitute values in this step. You can see that we have substituted all the values, and the value of q here also, overall efficiencies also they have given, which is 75%. uh, you will get the value of discharge is 2.644 meter cube per second. 2.644 meter cube per second is the value for discharge at inlet. Okay, now by using the equation of q equals to pi d1 b1 vf1, pi d1 b1 vf1, we can find out the value for b1, width of wheel at inlet, by using q is known quantity, d1 is known value, also vf1 is known value. So substitute the values of known quantities here. You will get the value for width at inlet as 0.177 meters. 0.177 meters is the value of width at inlet. Now this is about the uh, turbine, which is Francis turbine, and the calculations of Francis turbine. Now we'll move further for second type of turbine, which is axial flow reaction turbine. Okay, axial flow reaction turbine. Now this is axial flow reaction turbine. In previous part we have studied the radial flow reaction turbine. In radial flow reaction turbine, what happens, the water will flow in the radial direction. Okay, now here in axial flow reaction turbine, you can see that the name of this turbine will indicate only the direction of flow of water. Okay, here in axial flow reaction turbine, the water flows parallel to the axis of rotation of shaft. Okay, so that it names as axial flow turbine. Okay, and also, as this is reaction turbine, the energy which is available is not only kinetic energy but also the pressure energy. Okay, if it is impulse turbine, then only kinetic energy will possess at inlet, but the as this is reaction turbine, is it possesses kinetic as well as pressure energy. Okay, so axial flow, that means the water flows uh, parallel to the axis of rotation, and if the head at inlet of turbine is the sum of pressure energy and kinetic energy during the flow of water through runner, as a part of energy is converted into kinetic energy, then the term is called as axial flow reaction turbine. Okay, this is the combined definition of axial flow reaction turbine. Now, for the axial flow reaction turbine, the shaft of turbine is vertical. Okay, for the axial flow reaction turbine, the shaft of turbine is vertical. In this diagram, you can see the shaft is given which is in vertical direction, and vanes are given which are attached to the shaft. Okay, if you see, the diagram is somehow different than other types of turbine. This part is known as hub. Okay, this hub is also known as the boss. Okay, this is the lower end of shaft, uh, which is made larger. Okay, lower end of shaft which is made larger, and it is known as hub or boss. Okay, the vanes you can see are fixed on the hub here, and hence the hub act as a runner. Okay, in other types of turbine, the runner holds all the vanes. Here the hub holds all the vanes. So this hub or boss will act as a runner for axial flow reaction turbine. Okay, now for this axial flow reaction turbine, again there are some important types, subtypes, in which first is propeller turbine and second is your Kaplan turbine. Now, propeller turbine and Kaplan turbine, I'll explain it. When the vanes are fixed on hub and they are not adjustable, the turbine is called as your propeller turbine. Okay, when these vanes are um, fixed on the hub and they are not adjustable, then it is propeller turbine. But if the vanes on the hub are adjustable, then that turbine is called as your Kaplan turbine. Okay, that means propeller is not adjustable and Kaplan is adjustable. Okay, this Kaplan turbine, which we have I have explained, this Kaplan turbine is named after the uh, Austrian engineer, sorry, which is V. Kaplan. Okay, this Kaplan turbine is suitable where a large quantity of water at low head is available. Okay, where the large quantity of water at low head is available. This figure which is shown here is the Kaplan turbine, um, on which the adjustable vanes are fixed on the hub. Okay, now the main parts of Kaplan turbine. Main parts of Kaplan turbine are scroll casing. Second is guide vane mechanism. Third is hub with vanes or runner of turbine, and the last is your draft tube. Okay, draft tube. Now I'll show you the next diagram here. These are the components of your Kaplan turbine, where draft tube is shown, scroll casing is shown, guide vanes here and here, guide vanes are shown. Also the shaft is highlighted, in which boss is there. These are the runner vanes. These. Now the water from penstock enters the scroll casing here, enters the scroll casing and then moves to guide vanes. Okay, from both the ends it will move to, sorry, this is scroll casing. From this penstock water will enter and it will move through guide vanes. From guide vanes the water turns through 90 degree and flows axially through the runner. Okay, from this it will flow axially through runner. The discharge through runner is obtained by using the general expressions. I'll show it in the next slide. The inlet and outlet velocity triangles are drawn at the extreme edges of runner vane. Okay, corresponding to these points 1 and 2. This point 1 and this point 2. Okay, now the discharge for this type of turbine can be found out by using Q equals to pi by 4 d naught square minus db square, okay, into vf. This is printing mistake, vf, d naught cube. Now here d naught or do is the outer diameter of runner. In this diagram you can see outer diameter of runner, and db is the diameter of hub or diameter of boss. Okay, so it is named as db. do is nothing but your outer diameter, and vf is as usual the velocity of flow at inlet. Okay, now here you can see the draft tube also. Draft tube, I hope you have remember what is draft tube. Draft tube is nothing but the pipe of increasing diameter, large pipe of increasing diameter, which is at the uh, exit point, which is provided at the exit point. Now secondly, peripheral velocity at inlet and outlet. Peripheral velocity at inlet and outlet can be found out by using the term u1 equals to u2 equals to pi d naught n divided by 60. Pi d naught n divided by 60, in which d naught is the outer diameter of runner, that is do is the outer diameter of runner, and n is nothing but your speed, okay, which is given in revolutions per minute. Secondly, the velocity of flow at inlet and outlet are same here. Okay, so vf1 will be equals to vf2. Now the fourth point is area of flow at inlet is again equals to area of flow at outlet, and which can be found out by using pi by 4 do square minus db square. Okay, do square minus db square. Now these are about the important points which you have to remember while calculating the while calculating the discharge and velocities for Kaplan turbine. Okay, now we'll move further for the numerical of Kaplan turbine. Now, first numerical is Kaplan turbine working under a head of 20 meters develops 11,772 kilowatt shaft power. The outer diameter of runner is 3.5 meters and hub diameter is 1.75 meters. The guide blade angle at the extreme edge of runner is 35%. The hydraulic and overall efficiencies of the turbines are 88% and 84% respectively. If the velocity of whirl is 0 at outlet, then we have to determine first runner vane angles at inlet and outlet at extreme edge of runner, and secondly the speed of turbine. Okay, here runner vane angles at inlets and outlets we have to find out, and also the speed, that is n, you have to find out, that is theta and phi vane angles at inlet and outlet, and n is nothing but your revolutions, that is speed. Now in this problem, Kaplan turbine is there, head is given which is h equals to 20 meters and the shaft power is 11,772 kilowatts. Okay, now the outer diameter of runner, that is DO, is given as 3.5 meters, and also the hub diameter, that is dB or a boss diameter, is given as 1.75 meters. Okay, now the guide blade angle at extreme edge of runner is 35%, that is alpha is given as 35%, hydraulic efficiency is given as 88%, and also the overall efficiency is given as 84%. Okay, now the velocity of whirl at outlet is given as 0, that means the outlet has the radial discharge, so beta is also 90 degrees. Okay, because of that, here the outlet velocity triangle is like this. It is same as that of for the Francis turbine. Now here firstly we have to find out the value of discharge here. So for that, the overall efficiency is given by using the relation of overall efficiency, that is shaft power divided by water power. We can find out the value of discharge. Okay, so the value of discharge will be by using this shaft power by water power, and water power can be calculated by rho GQH divided by 1000. Okay, in here the overall efficiency is known, which is 84%, shaft power is given, and the head is given. So substitute all the values, you will get the value of discharge as 71.428 meter cube per second. Okay, meter cube per second. Now by using the velocity discharge equation which is given for the Kaplan turbine, by using that equation we can find out the flow velocity at inlet. Okay, Vf1. So Q will be pi by 4 d naught square minus dB square into Vf1. Here d naught and dB is known. Discharge we have find out. So the velocity of flow at inlet will be 9.9 meters per second. Okay, 9.9 meters per second. So this value we have find out for the finding out value of Vw1. Okay, that is world velocity at inlet. Now by using the relation of tan alpha from this diagram, you can see tan alpha will be Vf1 divided by Vw1. Okay, Vf1 divided by Vw1, and alpha is known, so we can find out the value of Vw1 as 14.14 meters per second. Okay, now we have already aware about the relation of hydraulic efficiency, which is eta h is Vw1 u1 divided by gh. Okay, by using that equation we can find out u1 value. So u1 will be 12.21 meters per second. Okay, because only this term is remaining here because Vw2 is 0. Okay, now the vane angles runner vane angles at inlet and outlet at the extreme edge can be find out by the velocity triangles, and that tan theta will be Vf1 divided by Vw1 minus u1. Now these all terms we have find out earlier. Substitute the values here, you will get the value of theta as 78 degrees 58 minutes. Okay, and for Kaplan turbine, as I have shown, the peripheral velocity u1 will be equals to u2 and vf1 will be equals to vf2. So from outlet velocity triangle we can find out tan phi as vf2 divided by u2. Okay, tan phi here, tan phi will be vf2 divided by u2, opposite divided by adjacent. Okay, so the tan phi value will be 39 degrees 2 minutes. Okay, these are the two angles we have find out. Now the last question is speed of turbine. So for finding out speed of turbine we can use the value of peripheral velocity, which will be pi dn upon 60. Now here d is your outer diameter, that is d naught. So pi d naught n divided by 60 will be your u1 or u2. Now here in case of Kaplan turbine, u1 will be equals to u2. So 12.21 will be pi dn n upon 60, in which the n value is only the unknown, which is speed. So substitute remaining values here, you will get the value of speed as 66.63 revolutions per minute, which is 63.63 rpm. Now this is about your Kaplan turbine and Francis turbine. Now in next video we will move for the part draft tube and the unit quantities. Okay, so up to this all the turbine parts, all the types of turbine which we have covered and the numericals we have covered on it. I hope you understand the Kaplan turbine, Francis turbine, also the impulse and radial reaction turbines, and the efficiencies of turbine too. Thank you.